Hello. Hello, Savitha, can you hear me?
Oh, sir, I didn't see that I was muted.
Okay. All good. My audio is clear.
Yes, sir.
Okay, finally, I checked your paper. You made some very silly mistakes, right? In some problems
Yes, sir.
where you lost the mark. Uh, okay, there are some things that I want to make some comments on some problems. Like this is good. It's fine. You did not lose. Now, in this problem where you were supposed to calculate the force here, diagram is perfectly all right. No problem with this thing. Uh, you got full marks, but you could have simplified this thing further. Just see this thing. F1 is equal to 2q square by 4 pi epsilon naught L square. You have got this thing. F2, you got this thing. And then you see, you did this thing, which is quite complicated, right? Although you got the correct answer, you will always get the right answer from me. But you know the right technique to do this thing. Just see that. Is there any relation between F1 and F2? Can I write F2 is equal to 2F1?
Yes, sir.
So in that case, when you use this thing, write F2 as F1 squared. Get the answer in terms of F1 squared. Like in this case, you could have simply done this thing that F1 squared plus 2F1 squared plus um, 2F1 2F1 cos 120 degrees. That was the thing. And then if you just go on solving like this is f1 square plus 4f1 square plus 4f1 square minus half. That is equal to this is 2, this is 3f1 square root over. That is equal to root 3 f1. And now simply root 3 and f1 is equal to what? 2q square by 4 pi epsilon naught L square, right? So you got the same answer. 2 root 3 q square by 4 pi epsilon naught L square, right? See, you got the same answer here. At the bottom, you got the same answer exactly, but there are chances of making a mistake when you deal with such kind of complicated expression, right? You may make mistake. In this case, you did not make mistake, but there are chances. Why make it so complicated when you can done it in a simple way? Yeah, this thing.
Yes, sir.
Yeah, this is not wrong, but this is the better technique, right? This is one thing. Okay. In this case, here this is perfectly all right. Diagram is perfectly all right, and everything's all right. Here I missed one thing. Consider a unique positive charged infinite plane thin sheet. Draw a cylindrical Gaussian surface. Let the surface charge density on either side correct. This is correct. Consider the point P at a distance A from which electric field is to be calculated. Correct. The curved surface of the cylinder is parallel to. Okay. Here, before you say this thing, you have to write one thing. By symmetry, electric field is always, you can simply write this thing. By symmetry, electric field at any point is always perpendicular to the sheet. I
Okay.
explained this thing right here because just see that if you take this point as P, so it divides it into two halves. So it is infinite on this side and infinite on this side also. So electric field is actually coming like this, but vertical components get cancelled out. They get cancelled out. Let us say that this is E, and this is, let us say that this is theta. So this is E cos theta. E cos theta will be on this side, and E sin theta will get cancelled out. So at any point, the net resulting electric field is, no matter where we are talking about, it is always perpendicular to this thing. Why? This is symmetry because it is an infinite plane. So
Okay.
at the top, there is equal number of charges. At the bottom, there are equal number of charges. Because of that thing, electric field will always be uh, perpendicular to this thing. So if I talk about electric field here, this will be like this, uniform electric field, and this is perpendicular to this thing, right? Always. So you have to mention this thing as well here. Then you go for this thing. Curves. Now, once you have decided what will be the direction of electric field, electric field is always perpendicular to the sheet. Once you have decided that, once you have decided this thing, then you can draw a cylinder Gaussian surface, right? You choose your Gaussian surface, and then you can see this thing that the curved surface, um, electric field is perpendicular to the curved surface area.
Okay.
ds vector will be in this direction and electric field is in this direction. Now they are perpendicular to this thing. That makes sense now, right? This is the thing. And the curved surface area of the cylinder is parallel to the electric field. Correct. This is now, this makes sense. The electric field is due to the two circular. So curved surface area does not contribute to the flux. It so it does not contribute to the net flux. Something. The electric field is due to the two circular caps only, and then you can do this thing that E times 2A. What did you do in the first is area of the E times, okay, 2 times E, right? 2 times E. Here, this is just see that you could have taken this thing phi 1, phi 2. Phi 1 is also EA, phi 2 is also EA. That is the thing.
Mhm.
So net flux is equal to phi 1 plus phi 2. Or left, right, you can say this. You can say this thing. This will be 2 times EA. So that's all right here. Why you wrote this 2A?
So because the same thing, the two area.
Two areas, right? Electric field is same. Yeah, that's all right. But write down like this, right? In this case, you're mentioning that first surface is contributing EA flux, second surface is contributing EA flux, and then you take the summation. Or you could have simply written this thing phi 3 also. Mention this thing also because EA, and this is 0, right? Then you are mentioning that the curved surface area is not contributing any flux to it. Always mention this thing, right? So phi 1, phi 2, and phi 3. There are three surfaces So you have to mention all of these things here, phi3, and just mention this thing here that this is EA, this is EA, and this is 0. That is 2EA, and that's it, right? And then you
Okay.
go for, then everything's all right. You got this thing that this is 2A sigma A by epsilon naught. Okay, from 1 and 2, yeah, here you just mentioned this thing that why did you write this thing? You have done, okay, you have done this. Using by Gauss laws, Q, here mention this in a Q enclosed, right? Mention that
Okay.
what is this Q, right? This is enclosed charge. Because there are
Okay.
charges outside also, so enclosed charge is very, very important. Q enclosed, and Q enclosed is equal to sigma A by epsilon naught. And now everything is all right. So in the
Okay.
board exam, no charges will be, no marks will be deducted. These are important points, right? These things are clear.
Okay.
So this is one thing. Okay. Um, this was a. Let me get the question to this one. Which question is this?
15. 15A.
Here you made a very silly mistake. This is the question. Okay, what were you thinking when you wrote this thing? 4 pi r square.
Sir, I took the curved surface area for no reason. Of a
Curved.
sphere.
Okay.
The formula I
Curved
wrote wrong.
surface. Yeah, that's why I said that you always have to write down this thing, right? That this surface is continuous. Suppose you're writing this FL.
I actually took the formula for area as 2 pi r square and I ended up multiplying by 2 since there are two caps. I ended up getting 4 pi r square.
Okay.
The
2 pi
formula I wrote
r square h, right? 2 pi, if you 2
so
pi
pi r
RH,
square.
right? 2 pi RH. If you think, uh, if this is the case, this is a cylinder. So this area, base area is equal to what? Base area is equal to pi r square. And
Yes,
curved surface area, curved surface area is equal to um 2 pi r h, right? This is the height of this thing that will be. So in this case, also you were supposed to do like you could have taken this thing phi one, phi two, phi three like this. So just take phi one, phi two, or you can say let us say this is the curved surface area phi c. No problem. Right, left, right, and curved surface area. So curved surface area will definitely play zero role because this is perpendicular to this thing, right? This is already given to you in the problem itself. Now in this case, what were you supposed to take here? Simply pi r square, right? You did not have to take this 4 pi r because you're talking about phi L. This is the area, right? What is the area of this thing? Pi r square. This is a circle. Simple. Pi r square. Area is equal to pi r square,
yes, sir.
right? So that was the mistake. That is why you got it wrong.
Yes,
Silly
sir. I
mistake.
would have got double the answer.
Yeah, and here also the same mistake. That's why this is also wrong. And here, phi net always include all the surfaces here. curved surface also, right? Although it is contributing 0, but mention it when you're
But no,
calculating the net.
for the 5 left, I got negative answer, but the answer given was positive in the answer key.
Yeah, it is. No, it should be. It is. It will be positive. Just see this thing. Why it will be positive? E, right here. Uh, in this case, everything's all right. Only pi r square is only 4 should not be the case here, right? Only 4.
So
There should not be any.
flux right, I took positive. Flux left, I took negative.
No. Flux. Outward flux is always taken as positive. Inward flux will be taken as negative. Just see this thing. Electric field is already given to you as here. This is not 2 I cap. Left will be minus 2 I cap, right? This opposite direction, right? If this electric field is 200 I cap, this electric field will be minus 200 I cap. This is opposite to that electric field. Given electric field is equal to this much, and here it is also given minus 200 I cap. It is already given in the problem,
Yes, sir. So
right?
I took it as negative.
Yeah. And delta S cap here is positive, and here delta S cap is negative. Area vector here will be negative minus I cap direction, right? So that is the thing. So in the first case, you were supposed to take I cap. I cap is correct. This thing is correct. But in this case, minus here and here it is minus this thing. So you were supposed to take minus 200 I cap times, this is one thing, and pi r square minus pi r square I cap.
So
That is
one
the
minute,
thing.
can I see what I wrote up in the file, right?
Yes. Here minus 200 I cap because electric field is in something like this, right? This is this thing. So here, this is the thing. This is the electric field here, and here electric field is in this direction. Obviously, this is in I cap direction, and this is in minus I cap direction. Delta S vector here, delta S vector here is equal to pi r square I cap, and here it is opposite to this thing. So how can the direction be the same? Delta S vector here pi r square minus I cap, right? You can write like this. This is the thing. Right, left. They are opposite direction. But the flux is positive. Just see that minus minus will cancel out and this will become positive eventually. Just see that one thing remember, if the flux is outward flux will always come out to be positive. Always come out to be positive, outward flux. Inward flux will be negative. If there is a circle like this, if the field lines are coming out of it, this is outward flux, right? Flux due to this thing will be this thing. And if the field lines are going in, so it will be minus phi, it will be plus phi. Net flux will be 0. If I say that there is a sphere, field lines are going like this. Let us say this thing. What is the total flux? What is the net flux? So total outward flux, total inward. This is outward flux, total inward flux. Number of field lines going out will be taken as positive plus 3. If I take it this thing inward minus 3, that is 0. Okay. I just calculated the number of field lines, but eventually like you have to calculate EA cos theta, right? That is the thing.
Okay.
So here, simple, just one mistake you made. Use the vector rules. For a single diagram, I cap, x-axis, y-axis is already given to you. So along the x-axis is the I cap. Opposite to the x-axis is the minus I cap. Simple. right? So here E and S both are directed in the same direction. So I cap direction. Here E and S, delta S are directed opposite to the x-axis. So they are both minus I cap. So if you multiply these two things, eventually you'll get the positive number. Minus minus will become a positive number, right? So net outward flux is not zero. This is wrong, right? So here, let us just calculate this thing here, whatever is the case. In terms of pi, we want to calculate this thing. So 4 will not be there. 5 to the 10. Okay, no, no, no. This thing 25, this thing, right? So 4, it will just be 2. Um, Now this will be plus 5 into 10 to the power minus 4. And that will be the case. That is equal to 0.5 pi. 0.5 pi. That will be your answer. Okay. ये Newton per coulomb meter square. That is the thing. This is one thing, and I think you will also get here also. If you multiply this thing, you will also get the same thing. 0.5 pi Newton per coulomb meter square. So it will be double of that thing. 0.5. So this will be 0.5 pi plus 0.5 pi plus 0. That is equal to simply pi Newton per coulomb meter square, right? If I haven't made any calculation mistake, then this is the right answer. Net flux is not zero.
Okay, sir.
Is that clear? This one?
Yes, sir.
So that is one thing. And okay, she gave you the, this is just the ABC, right? Same question.
So this question you taught in class after that.
Yeah, you have understood this thing, right? Simply
Yes, sir.
just, I think you had confusion in finding out the direction of electric field here. I think you got it right now. Here, there should not be any confusion. So, what was the question here actually?
It's actually supposed to be plus instead of minus.
Yes, this is the question. So two charges plus 1 coulomb minus 3 coulomb, 20 centimeter apart in vacuum. What is the electric field at the midpoint? Yes, this is correct. Yes, I think the confusion, right? I told you never to take the sign of the charge, right?
Yes,
That
sir.
is the mistake. So never to take the sign because sign just tells you the direction, but the direction has already is already understood here. So that is the mistake. B part, if the negative test charge is of magnitude this thing placed at this point, what is the force experienced by? Just QE, right? QE, whatever is the electric field? That is here you got zero. That is why there is a mistake. Otherwise, this would have been right? This will never be. This is not equal to zero. There will be a definite number in this case, right? That is the thing. And then this approach is correct. This is correct. You have to take that thing. But since you calculated electric field as zero, your force is coming out to be zero, and that's why this is wrong, right? But that formula, that approach is good. F is equal to QE, you have to do. And this one, these things you did beautifully well. No problem with these things. That's it. Nothing else. Just small mistakes. You have to correct those things, and you'll get the full marks.
Yes, sir.
So when is your test? Physics test?
Sir, 5th June.
5th June. Okay.
Test is starting for
Fifth.
first, but physics is on 5th June.
Okay. So let's come back to our how much we have covered.
So we were in last class, we did the magnetic force and the current carrying conductor, and then we also did the pitch.
Okay, these things, right? We did some problems. Is that clear how to do these things?
Yes,
IL
sir.
cross B, how to find out the directions of these things. See, it is just the application of vectors that you have learned, right? If you know vectors well, these are just very simple problems. They look very difficult, but they are not. Today we'll do Biot-Savart law. We have done everything, right? That is the thing. IL cross B, we have done that thing. We have done this one. IL cross B, magnetic force, yes. We're doing fourth chapter. Did you start these things at your school?
So they are yet to start with the Biot-Savart law.
Okay.
We have completed what we've completed so far.
How much? How much they have completed?
Sorry, sir.
How much they have completed?
This is what we have completed so far.
Let's do Biot-Savart law here. This is the most important law here for this chapter. Let us say that this is a wire. This is what is given to you. So one thing is, first you note down this thing that we know that any current carrying conductor produces a magnetic field, right? Any From the Orsted experiment, now it is very, very obvious for us that any current carrying conductor produces a magnetic field. Any current carrying conductor produces a magnetic field around itself. And Biot-Savart law helps us to find out how much magnetic field is produced by a current carrying conductor. Okay, that is the thing. So just like it is something like this. If there is a positive charge and there is a negative charge, they apply a force on each other whenever they are brought in contact. Whenever they are brought in contact with, not if they are brought closer to each other, they apply forces on each other. How do we measure the force? Coulomb's law, right? Coulomb's law. Coulomb's law helps us to find out that exactly how much force they apply on each other. Similarly, if a current carrying conductor produces a magnetic field around itself, so at any point, exactly how much field is produced by the current carrying conductor is given by Biot-Savart. That's it.
So how much field is
Yeah.
produced by current conductor?
Yeah. How much field means magnetic field is what? How do we measure the magnetic field? Magnetic field is measured in Tesla, right?
Yes, sir.
Measured in Tesla. So exactly how much magnetic field? Just like this thing. If the positive charge and negative charges are applying forces on each other, exactly how much force they are applying on each other? Maybe it is 10 Newton. So equal and opposite charges, this is also 10 Newton. Similarly, if the current carrying conductor is producing a magnetic field at any point, so how much magnetic field it is producing? So it is giving you the magnitude of the magnetic field. So far, we did not know about the magnitude, right? If the field lines are given to you, you know that magnetic field lines are like this. Like you can know that here P and here it is Q. So if I say that where is the field stronger, BQ and BP, where is the field stronger? BQ is stronger, right? Because field lines are closer. But if I ask you what is the magnetic field at Q, then you don't know, right? Absolute magnetic field, you don't know. So such kind of calculations can be done with the help of Biot-Savart. Simple. So it gives you the magnitude of the it it helps to calculate the magnitude of the magnetic field. Calculate the magnitude of the magnetic field. Okay, let us say that the statement, proper statement. Uh, in NCRT book, it is directly given, but will not be using that thing much. Let's see this thing. Magnetic field due to a current element. If I directly use this thing, directly use the uh, directly use the statement of the NCRT book, then it simply says that consider an infinitesimal. Okay, let us say that the current is flowing. Just say the direction of the current is given to you. Current is flowing in this direction in this wire. It could be anything, that the wire can be bent in any direction. So just remember that the magnetic field due to a current carrying conductor depends on the shape of the conductor. Right. One thing is this thing before this statement. Magnetic field due to a current carrying conductor depends on its shape. It means, just see that if the straight current carrying conductor is there, you already know these. It produces a concentric field line, right? If you bend the wire like this, what kind of magnetic field is? There is a circular loop and the current is flowing in this direction. So it produces a magnetic field like this. This case, yes, something like this. This is the magnetic field, and if there is a solenoid, you already know this thing, that if there is a current in this case. So this is something like this, this. This is North Pole, this is South Pole. This will be producing a magnetic field like this. It's something like this. You know these things. They never cross each other. So if you change the shape of the conductor, magnetic field will also change, right? That is the thing. Magnetic field lines around it is changing. It means the magnetic field is changing. Simple. So, but we do not need to do this thing here. Simply let us just talk about the statement here. Biot-Savart law statement. Statement. NCERT statement. The small magnetic field due to a current element field dv vector due to a current element I dl vector. Let us say that I dl vector is directly proportional to Um, I dl vector cross r vector divided by r cube. That's it. Means simply db vector is directly proportional to I dl vector cross r vector r cube. That is the thing. So if you remove this proportionality sign, mu naught by 4 pi comes as the this thing, and this is I dl cross r vector divided by r cube.
So, but how did it get its proportional to this?
So this has been done. This is a law, right? By experimentation, it has been found that whenever you're trying to find out the magnetic field, it has been found that directly proportional to this thing. Where just first write down these things, then I'll explain everything. Here, r vector is the position vector of the point, where the field is being calculated. Ideal, you cannot separate them, right? They are always together. This is called current element, and r is the distance of current element from the point. From the point. Or we can, so this is the NCERT statement of this, right? But in reality, that the law that we have to use, which we will use in derivations of the things, we'll use exactly the same thing. This is more accurate. The laws expressed in vector forms are more accurate, precise, and they contain more information than the scalar one. But in many cases, whenever doing the calculations, we are using the scalar form of it. So this is a vector form, right? This is a vector form. Tell me, what did you not understand?
So, the difference between r vector and r.
R vector, right? Okay, just see that. If you're taking the wire something like this, current is flowing in this direction now. I take this thing, I. So you will just cut out a small section of it, DL, right? And since the current is flowing in this direction, what is the direction of the current? Current is in this direction, right? So this is a DL vector. This vector will be called DL vector. IDL vector, sorry. This is called IDL vector. This is called current element, right? And this current element is so small that you can treat it like a point charge. Current element IDL vector is very small, can be treated like a point, just like a point charge, right? Its shape and size is completely neglected. Here, ideal vector, the size, the it is very small, so it will be treated like a point. So just think about this thing, that there is a point here. This is ideal point, ideal vector, and suppose I want to calculate the field over here at this point. I want to calculate the field at this point due to this current element. So we divide the wire into infinite number of current elements. Now our current element is this. This is the thing. So first of all, what I'll do, I will find the position vector of this point. This is the position vector. This is R vector, position vector of this point P, and this is ideal element, right? Simple. Now, in this case, here exactly how much field is produced by this ideal element? dB vector. dB vector. Now, how do we find out this dB vector is equal to how much? Mu naught by 4 pi I dl cross r vector divided by r cube. R cube is just the magnitude. Now, tell me what is the direction of this magnetic field? Can you tell me what is the direction of this magnetic field? You know this is cross multiplication, right? Cross product of the vector. You know the direction of dl vector, r
In this,
vector. Yeah. What is?
sir, I'm getting this concept.
Not getting the concept?
No, sir.
Okay, okay. Just see that it is the just see that it is just a statement. You just need to understand the terms, each term, what they mean, right? This is just a constant. This is just a constant. Here, mu naught is called the permeability. This is very important. We'll talk about it later. Permeability, just like permittivity, exactly whatever you have got for the same kind of expressions you will get for the magnetic field as you have got for the electric field. So just like permittivity, it is a permeability of the medium. Magnetic field also depends on the medium. For different medium, magnetic field will be affected. Ideal cross mean by current element. This is current element. Did you understand current element? Simply just cut out a small piece and in the direction of the current, take the vector. That is your ideal vector. Anyway,
Okay.
if you cut out this thing here, like suppose dl vector is here. So this is the direction of ideal vector.
Yes, sir.
Tangent to the current carrying conductor. That is ideal vector, right? It's very simple. So here, what is the point? We are just cutting out a small piece. Here, the current element will be in this direction, ideal vector, something like this, right? So at every point, dl vector is different because the direction of current and this thing will be different, right? At every point, here it is different. See that here it is given like this direction. Okay. So at this point, if I ask you to this thing, what is the direction of the what is the direction of the magnetic field? What is the direction of current element? It is in this direction, right? This is ideal vector and this is magnetic field. Now just use the cross product ideal cross r vector. What is this thing? Right hand thumb rule. Ideal vector is in this direction. Ideal vector is in this direction. And the r vector is in this direction. It is on the screen. Tell me, what is the direction of the magnetic field? At this point, right? At this point, we are trying to find out the magnetic field. Magnetic field at that point is dB vector. What is the direction of this dB vector? How do we find out the direction of cross product?
Sir,
You know,
inwards.
inwards, right? Correct. Ideal cross. So ideal to R, curl your finger inwards, no,
Out,
outward, right?
outwards.
Outwards, correct. So magnetic field will be just outward, right? This is the dB vector. This is out of the screen. Simple. You got it? So this is the magnetic field due to the current element, not the entire thing, right? if you want to find out the magnetic field due to the entire current carrying conductor, you have to integrate this. Simple, right? So this is the magnetic field dB vector is equal to mu naught by 4 pi into I dl cross r vector divided by r cube. This is the magnetic field due to the current element. Into a current element. The magnetic field due to the entire current carrying conductor is given by just the integration of dV vector. That's nothing. Clear this thing? If you take the integration of this thing, then the magnetic field can easily be figured out due to anything. One example I'll take, then you'll understand this thing. Let us say that this is the straight current carrying conductor. And in this case, the current is flowing in the upward direction. I. Okay. And I want to find out the electric field at this point. P. What is the direction of electric field at this point? Can you tell me?
Outwards.
Outwards. So
Yes,
you're
sir.
saying that, okay. So let us just apply the Biot-Savart law here. dV vector is given by what? Mu
Sir, it's
naught by
outwards.
outwards, inwards. Decide this.
Inwards.
Inwards, right? R
Yes,
cube.
sir.
Very simple, you have to find out ideal and R vector. So you can cut out ideal vector at any point. Doesn't really matter where. Let us say that DL vector is this thing here. I DL vector will be this direction. Just calculate the position vector of this thing. This is the position vector of this point. IDL vector is in this direction, right? This direction. IDL vector. IDL cross be inward, right? Just coming inward. Yes. Just into this field. dB vector. So if I integrate over this entire this straight current carrying conductor, which we have to do, then we will easily figure out the direction of the net magnetic field at this point. Clear? This thing.
Okay.
Similarly, can you tell me what is the magnetic field at this point? Direction of magnetic field using this law.
Outwards.
Outwards, right? Correct. This is outward. So one thing, one very important thing you already got this thing. If there is a current carrying conductor, so on one side, it produces a magnetic field out of the screen. On the other side, it produces a magnetic field into the screen. But we know that it produces actually a concentric circle, right? That is the magnetic field. And if you apply the right hand thumb rule, just see this thing. Is it not the magnetic field line? concentric circle. It is always the case. Whenever you're doing this thing, concentric circle. Did you get this point? What I'm trying to say? Magnetic field lines are something like this. So on one side, the magnetic field line is into the screen. On the other side, it is out of the screen. Curling of the curling of the fingers, right? Straight current carrying conductor, and you're holding the fingers like this. So it is circled like this, right? So on the screen like this here. So if you curl your fingers, it is your fingers are coming out of the screen on this side, and here it is going into the screen, right? Out of the screen into the screen, something like this. So on one side out of the screen, one side out into the screen, something like that. Tell
Yes,
me if you
sir.
got this point. Got it?
Yes, sir.
This is the thing. So this is a direction, but magnitude also, right? So new statement. If I so dB is equal to what? If I use the magnitude of this thing, since in exam you will write exactly this statement, no problem. This is NCRT statement. They have used this language, right? Simply. So use this thing here. One thing I forgot. What is the value of mu naught? Permeability. And permeability has value is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. Yeah, this is the thing. How we calculate this thing, Tesla meter per ampere. Um, you can easily figure it out from this thing, right? From this thing, what is the unit of this thing? Tesla. These are just constants. This is ampere. This is meter. This is meter, and this is meter cube. So you can see that Tesla meter per ampere, right? You can easily figure out the dimensions of mu naught from this formula,
Okay.
right? So what is the magnitude of this thing? See that since dB vector is equal to mu naught by 4 pi I dl cross r vector divided by r cube. This is the vector form. If you just calculate the magnitude here, dB will be equal to mu naught by 4 pi I dl sine theta r square, isn't it? That will be the case. In this case, just see that dl cross r. What is the magnitude of this thing? dl r sine theta, right? And at the bottom there is r cube. R, this will become r square. That is it. Any confusion here?
Yes, sir.
So another alternative statement is this thing. The magnetic field due to a current element ideal is directly proportional to directly proportional to the current element magnitude of the current element, or you can simply just say that not magnitude, right? Simply proportional to the current element and sine of the angle between the current element and the uh, position vector of the point and inversely proportional to the inversely proportional to the square of the square of the distance between the current element and the point. This is what we are going to use for the derivation. Point is very, very clear, right? If there is a current carrying conductor is given, you simply have to cut out a current element at any point. This is your current element. Let us say that this is your current element like this, ideal vector. And wherever you want to find out the magnetic field, that point, you have to take the position vector of that thing. This is your R vector. That is R distance. And the angle between them, this is the theta, ideal and R. Angle between them, right? So in this case, dB will be dB. Here you can clearly see this that dB is directly proportional to ideal. And it is also saying that dB is directly proportional to sine of the angle between them, theta with the angle. dB is also directly proportional to inversely proportional to the square of the distance between them. That's it. Therefore, dB will be equal to what? dB is directly proportional to I dl sine theta divided by r square. That is it. If you just get rid of this proportionality sign, this comes out u naught by 4 pi into I dl sine theta by r square. This is one of the statements. You can easily remember these things. Magnetic field is directly proportional to current element, directly proportional to sine of the angle between current element and the position vector of that thing, and it is inversely proportional to the distance between the current element and this thing. These are the three things that you have to remember. So magnetic field is inversely proportional to the square of the distance. What does that mean? As the distance is increasing, magnetic field is decreasing, just like electric field inversely as the square of the distance. So it follows inverse square law, right? Magnetic field obeys inverse square law. That is the thing. Yeah,
Okay.
this thing. You got the angle between this thing. Keep this thing in mind, right? What do we mean by this thing? Angle between this thing. So let's do now we'll do some applications of the Biot-Savart law. That is important. That is not given in your NCRT book, but the questions are mainly asked from there. So let's just do that thing. question. Mm, Okay, let's take one question. Try to solve this question. Draw the diagram. You can understand the diagram, then it is very easy for you to understand. Did you get the diagram?
And I'm not able to do this one.
Okay, let's just do this together. See, properly. You just tell me, right? What did you understand? Where you're not getting this? Let us say that this is uh, the magnetic field appears to be a little bit difficult than electric field. Just pay attention. If you know the vectors, then it is easy. East, uh, yeah. How do we represent the angle? East, west, east, west, north, south. The wire placed along the north-south direction carries a current. North-south direction carries a current from south to north. That's what I was doing. From south to north, so the current is flowing in this direction, right? I direction is in this direction. Find the magnetic field due to 1 centimeter piece at the 200 centimeter of 1 centimeter piece of wire at a point 200 centimeter northeast from the piece. Let us say that this piece of wire is this. The length of this thing is 200 centimeters given to you. And northeast side, it will be something like this. This is the point. This is 200 meter, 200 centimeter away. Sorry, 1 centimeter piece, right? My mistake. Mm, Let us say this thing. Hmm. This is the thing, and this is 1 centimeter, 1 centimeter of wire. Just see that. This is given 1 centimeter. This is 1 centimeter. And this is 200 centimeter distance away. Now, here at this point, what is the magnetic field? This is it. What is the magnetic field? It's simply mu naught by 4 pi I dl sine theta by r square. That's it. That is the magnetic field, right? Simple. So
Okay.
just put the values. Everything is given to you here. Mu naught I just gave you. What is the value of mu naught? Okay, I did not give you the value of this. Mu naught is equal to 4 pi into 10 to the power minus 7. This thing. This is the thing, right? This is the Tesla meter per ampere. That is this thing. 4 pi is given. So mu naught by 4 pi is just see that. Mu naught by 4 pi will be equal to what? Mu naught by 4 pi is simply equal to 10 to the power minus 7 Tesla meter per ampere. Right? That is the thing. So here in this case, just put the values. dV is equal to mu naught by 4 pi I dl sine 45 degree. It is northeast direction, right? Northeast direction. So that is 45 degree, right? This is 45 degree. And this is r square. Just put the values. This is 10 to the power minus 7. I is already given to you. I is equal to how much? 10 ampere. DL is given to you 1 centimeter, 0.01 meter. Sine 45 degree is equal to what? 1 by root 2 divided by r square is equal to what? 200 centimeter. That is 0.2 square. That will be your answer. That's it.
Okay.
Clear? Just you need to put the values here.
Like I'm confused which one should I take DL and which one should I take R?
Yeah. So DL, just see that it is a very long wire, right? It is a very long wire placed along this. You're just cutting out a very small section of it. So this is the current element, DL element, right? This is the current element. That is the thing. So that is the case. And just see that what direction, whatever is the answer is given to you as, let me just say this, 1.8 into 10 to the power minus 9 Tesla given. Can you give me the direction of it? What is the direction of this magnetic field?
Yes, sir. Inwards.
Inwards, right?
Yes, sir.
IDL cross B. Yes, correct. So this is into the screen. That's it, right? That is what you have to do. Take one more question from NCRT book. Take this.
What is it? 8 into 10 to the power minus 8.
Sorry, how much?
8 into 10 to the power minus 8.
The answer is given to you 4 into 10 to the power minus 8 Tesla.
I'm getting
See,
double here.
maybe you have made some mistake. See?
Oh, okay, I found what I did.
What is the mistake?
I took R cube.
R cube, right? R cube, no. R square, right? R square.
Yes, sir.
So I told you for most of the cases we'll be using this thing mu naught by 4 pi into I dl sine theta by R square. We'll be using this expression, right? We'll be dealing with this thing. That is the case. Okay. What is the direction? Direction
Inwards.
inwards. Uh, Current is in which direction? Is at the origin and carries a large current in ampere. Oh, direction of current is given in this direction. IDL is in this direction and this thing is in this direction. R vector. IDL cross R. This will be in this direction, right? Out of the screen.
Outwards.
Outwards. Correct. These things you understood how to do these things, how to find out the direction of magnetic field and magnitude is exactly magnitude is simple, just this formula. Okay, here there is important consequence of certain things. Let us just talk about this. Relation between epsilon naught and mu naught.
And also one more thing. So is there class in the evening?
No, no class in the evening, right? This is the evening class. Evening I'm not available. I'll not be at home.
Okay, sir.
So that's why.
Okay, sir.
So just see, if I multiply epsilon naught and mu naught here. Okay, but before that, let's see, what is the Coulomb's force? Question for the Coulomb's force. 1 by 4 pi epsilon naught q1 q2 by r square, right? Here and here, very simple, or we could have simply written this thing k q1 q2 by r square, where k is equal to what? 1 by 4 pi epsilon naught. That is equal to 9 into 10 to the power 9 um, Newton meter square per coulomb square. That is the thing. This thing you already know. Let in order to find out this thing, mu naught, epsilon naught, mu naught. If we multiply this thing, we can do one thing. Eps, uh, epsilon naught, mu naught, we can multiply and divide by 4 pi and 4 pi. Then that will give us 4 pi epsilon naught times mu naught by 4 pi. You can do this thing. Right? Exactly the same thing. Now you already know this thing. 1 by 4 pi epsilon naught is simply equal to 1 by k into this mu naught by 4 pi is simply equal to 10 to the power minus 7. So that is Um, K is equal to, we can write that 1 by 9 into 10 to the power 9. And then this 10 to the power minus 7 will become 1 by 10 to the power 7. That is the thing, which is equal to 1 by 9 into 10 to the power 16. Right? Or we can write this thing, epsilon naught mu naught is equal to this much. So epsilon naught mu naught is equal to 1 by 3 into 10 to the power 8 square, which is the speed of light. Epsilon naught mu naught is equal to 1 by c square. That is, c is equal to 1 by root over mu naught epsilon naught. This is the relation between epsilon naught and mu naught. They are related to so the permeability and permittivity are connected with each other. This is called electromagnetism. They are directly connected to each other by the speed of light. It means any electromagnetic field will move the maximum speed at which any electric field can move, electromagnetic wave can move is c, not more than that. Right? That is the thing. This is one of the relations between these things. Simple. Okay. This thing is clear. Tell me if you have any doubts regarding this session. Any point which is not clear.
No, sir.
This is Yeah. This is the most important one. Next class we'll be just doing the applications of this thing, like magnetic field due to a straight current carrying conductor, circular current carrying conductor. So far you just knew the basic ideas of these things which you have developed in the 10th standard, but here you will actually calculate the magnetic field, and the questions are asked based on this thing. Here, just like Gauss law, there is a very important law that we have to do, that is Ampere's circuital law, uh, and then solenoid. I think uh, in just two classes, this chapter will be over too. Till solenoid, exam portion will be covered in just two classes. Next class, I'll show you some applications of this Biot-Savart law, and then Ampere's circuital law, and then solenoid directly. Solenoid, toroid is not there, right, in the syllabus? Toroid is not in the syllabus.
So it's there. Solenoid is there.
Solenoid and toroid is not there, right?
It's not there.
Yeah. So in two
So for
classes,
this
most
exam, still
probably.
solenoid.
Yes,
So for this exam, it's still solenoid.
still solenoid, right? So, okay, that we can cover in just two classes. Maybe in next class also we can cover most of the portions in there. But some derivations are long, and we need to discuss those things. Ampere's circuital law is not. It is just like Gauss's law. It is very simple. And then once you understand this Ampere circuital law, solenoid, simple. Okay.
Okay.
So let me know if you're free anytime, tomorrow or someday. We can arrange the session, right?
Okay, sir.
Okay then. That's it for today. Bye.
Thank you, sir.